Hey everyone, so in this video we're going to be talking more about hypothesis testing, and we're going to go back to the idea of confidence intervals, but we're going to be doing it with two populations. And this video is one video of two, and this is going to be going over definitions and formulas, and then there's going to be another video that goes over some examples that involve this concept. So just a review of what hypothesis testing is. A hypothesis is a proposed explanation for some phenomenon, and we use hypothesis testing to objectively decide one way or another if the observations from a sample are significant enough to conclude whether or not a hypothesis is true. And remember, we had a null hypothesis, which was HO, and we had an alternative hypothesis, HA. And remember, we're basing all of our decisions on the null hypothesis. It's our baseline. We're assuming that it's true until we have enough evidence to go against it. And the way we check how much evidence we have against the null hypothesis is we check how extreme our test statistic is using either the critical value method or the p-value method, which both give equivalent results. Now, what if we took this idea and expanded it and looked at the difference between two means or between two proportions? So here's what's going to happen when we're doing hypothesis testing with two means. So first of all, we're going to use subscripts to denote which population each statistic or parameter is from. So for example, mu2 for the Pokemon fans is the population mean from the second population. Similarly, mu1 is the population mean from the first population. And between these two population means, we're going to have a hypothesized difference, and we're going to call this delta zero. And we'll get into what that means in just a second. So just like hypothesis testing with one mean, we're also going to have a null hypothesis and an alternative hypothesis that are structured in the same way, but now it's regarding the difference between the two means and not the actual means themselves. So an example of this would be this. So our null hypothesis is going to be that mu1 is equal to mu2, or that the population means are equal to each other. And an alternative hypothesis could be that mu1 is greater than mu2, or it could be that mu1 is less than mu2 or not equal to mu2. And then an equivalent way of stating this is that mu1 minus mu2 is equal to 0. Because if they're equal to each other and we subtract one from the other one, we're going to get 0. And then our alternative hypothesis is going to be that same concept, where if mu1 is greater than mu2, then when we subtract mu2 from mu1, then the result is going to be greater than 0. And the reason we might want to structure it like this is because then we can define what's called a delta zero. And the delta zero is that hypothesized difference, which is going to be this 0 here. So in this case, delta zero is going to be 0. So our usual assumptions need to be met for both samples for the test to be valid. So we're going to need N1, the sample size from the first population, to be greater than or equal to 30. The sample size from the second population needs to be greater than or equal to 30, and or the populations need to be normally distributed. And then the sample must be independent. These are all the same normality checks that we did before when we were dealing with one mean, so this is nothing new. So this is that tree diagram that we saw a couple videos ago that talks about when we should use Z versus when we should use T. And we went over that before, and the same concept applies here. So when we're conducting this test, we're going to have something that looks like this for our test statistic. And this may look a little bit complicated, but all we're really doing is we're taking that information from our sample, the sample means, the difference between the two, and we're subtracting that hypothesized difference, and then we're dividing by the standard error for the difference between the two, which is the same thing we did with one mean, except it's just expanded into the idea of two means. So remember when we did this with one mean, we were taking that sample mean, subtracting that hypothesized mean, and then dividing by that standard error. So this is the same concept, it's just a slightly different formula. So after calculating this test statistic, the usual critical value method or p-value method can be used based on a specified level of alpha. And then we're going to go over an example of this in the next video. So when the population variances are unknown, which is actually most of the time, we're going to be using t instead of z. So when we're using t, our test statistic is actually going to look pretty similar to what it looked like when we were using z. But there are some small differences here. Now, the first difference is that remember when we're working with t, we have to worry about the degrees of freedom here. We have to be careful with that. And when we're working with two populations, we're going to have two sample sizes. And the way we calculate the degrees of freedom with two sample sizes is to take n1 plus n2 minus 2. Now, one thing to note here is that the degrees of freedom from one population is n minus 1. So if we did n minus 1 plus n minus 1, we would come up with n1 plus n2 minus 2. So this is pretty much combining the degrees of freedom from one population with the other population. And then the other thing that's different about this formula is this SP squared right here. And we actually haven't seen that before. But SP squared is what's called the pooled variance. And all this is it's just a weighted average of the two sample variances, and we use it to provide the best estimate for the shared variance between the two populations. And the way we calculate this is to do n1 minus 1 times s1 squared. So this is the degrees of freedom from the first population times the first variance, plus the degrees of freedom for the second population times the second variance, divided by the overall degrees of freedom. So this is a weighted average of the two sample variances. And then when we find that, we put this into the formula right here. Now, one thing to note here is that we have to assume that the two population variances are equal, otherwise this is not valid. So now how about hypothesis testing for two proportions? So just like before, we're going to use subscripts to denote which population each statistic or parameter is from. And just like before, the hypothesized difference is going to be denoted by delta zero. And also, just like before, our hypotheses are going to be regarding the difference between the two proportions. So this is an example right here where our null hypothesis could be that P1 is equal to P2 versus an alternative hypothesis that P1 is greater than P2. This could be a less than sign or a not equal to sign, depending on what we're testing. And then equivalently, we could work the delta zero into this by saying P1 minus P2 is equal to 0, or an alternative hypothesis, which is P1 minus P2 being greater than 0, or less than 0, or not equal to 0, again, depending on what you're testing. And again, in this case, our delta zero is going to be the hypothesized difference between the two. So 0 is going to be our delta zero in this case. And again, just like before, the usual assumptions need to be met for both samples for the test to be valid. So both samples must be independent, and we need to have n times p greater than or equal to 5 and n times 1 minus p greater than or equal to 5 for both samples. So there's going to be a slight difference with hypothesis testing for proportions. So the formula for the test statistic depends on whether or not delta zero is going to be equal to 0. And in most cases, both in stats courses and in real life, our delta zero is going to be equal to zero, but there are some cases where it's not, but we're going to talk about the case where it is equal to zero. So if it is equal to zero, then this test statistic for the hypothesis test is going to look something like this. And again, just like when we were talking about with t, we're going to have this new notation here. And in this case, it's going to be called the combined proportion. And the combined proportion is exactly how it sounds. We're taking these two sample proportions and we're combining them. So if we had just one proportion, it would be x over n, but we have two of them, so we're combining the x's and we're combining the n's, and we're coming up with a combined sample proportion, which is p hat c, or pc hat, whichever one you'd like to call it. And the reason why we get to do this combination is because our null hypothesis assumes that these two proportions are equal to each other. So remember when we were talking about the pooled variance, we were assuming that the two variances were equal, which allowed us to calculate the pooled variance. And this is the same concept here. We're assuming that these two are equal under the null hypothesis, so that's what allows us to make this combination right here. And if delta zero is not equal to zero, then the test statistic is going to look something like this. And I'm honestly not even going to go over an example of this, but if you're curious, this is what this looks like. Okay, so we talked about hypothesis testing with two means or two proportions, but now what about confidence intervals with two means or two proportions? So remember, a confidence interval is an interval around a point estimate that provides an estimate for a population parameter with a specified level of confidence. So remember, we use sample statistics such as x bar or p hat, for example, as our point estimates. And then we built confidence intervals for population parameters like mu or p. So what if we took this idea and instead looked at the difference between two means or between two proportions, like with the hypothesis testing? So remember, with one mean, we constructed a confidence interval for mu, but with two means, we're interested in constructing a confidence interval for either mu1 minus mu2 or mu2 minus mu1, which is just the difference between those two population means. So as you might expect, the first situation we're going to be talking about is the situation with z. So just like before, the usual conditions need to be met here. We need to have an independent random sample, and then we need to have some way of justifying that this distribution is going to be at least approximately normal. So that could mean either the sample sizes are both big enough, or that the populations are both normally distributed, or both. And then the other thing here is that sigma 1 squared and sigma 2 squared both need to be known in order for us to be using z. And then in this case, a 100 times 1 minus alpha percent confidence interval for the difference in the two population means is going to look something like this. And again, this is the same kind of concept that we had before. This is our point estimate. So our best estimate of the difference between two means is going to be just the difference in the sample means. And then to build a confidence interval around this, we need our usual critical value and then the standard error for our estimate. So this is the same thing we've been doing before with confidence intervals with one mean, but now we're just expanding it and adding a little bit more to the formula. But the concept itself is the same. So when we're using t instead of z, we're going to have the same thing where we need to have an independent random sample, but now both populations need to be normally distributed, and the two population variances need to be unknown but assumed to be equal. And then our confidence interval for the difference in means is going to look something like this. And just like before, this is the same concept. This is the point estimate here, and then our usual critical value, and then a standard error. And then notice, just like with the hypothesis testing, we're going to have this pooled variance here because we're operating under the assumption that these two population variances are going to be equal. And because of that, we're going to pool the variances by calculating a weighted average of them using the degrees of freedom. So what about confidence intervals with proportions? So remember, with one proportion, we constructed a confidence interval for the population proportion P using the information from the sample. Remember, we took P hat as our point estimate, and then we built our confidence interval around that for what we think the true population proportion could be. And now with two proportions, just like with the means, we're interested in the difference between these two proportions. So just like before, we need to have our usual assumptions met here. Both samples need to be independent, and we need to have large enough sample sizes such that n times p is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5 for both of the samples. And if all of these assumptions are met, then our confidence interval for this difference is going to look something like this. And then I know I sound like a broken record here, but we're going to have this same concept where we take the point estimate for the difference in the two proportions, and then we're adding and subtracting this critical value times this standard error right here. So the idea itself is nothing new, but the formula is just changed ever so slightly depending on what we're trying to calculate. So anyway, that's it for this video. In the next video, I'm going to be going over some examples of some of these concepts, but for right now, these are the formulas and the definitions for working with two populations. So I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.